In our last video, we have derived expressions for torque and speed of DC motors. In this video, we will solve few numerical problems on torque and speed of DC motors. Before solving numerical problems, we will quickly revise important relations related to torque and speed of motors. So we have seen that the back EMF EB, it is given by EB is equal to 5 Pn upon 60 into Z upon a volt. In this case, N is speed in revolutions per minute. If it is in RPS, that is in revolutions per seconds, EB is equal to 5 Pn into Z upon a volts. And the back EMF EB is also given by V minus IaRa. Then the relation between power and torque. P is equal to 2 pi nt upon 60 if speed n is in RPM, and P is equal to 2 pi nt if speed is in RPS, that is in revolutions per second. Then torque developed in armature TA, it is 1 upon 2 pi 5 Pia into Z upon A, and 1 upon 2 pi is nothing but 0.159 if the speed is in revolutions per second. If the speed is in revolutions per minute, then TA is given by 9.55 phi Pia into Z by A. In this case, N is in RPM. So from these two equations, we can see that TA is directly proportional to the product of flux per pole and armature current Ia. Then the torque available at shaft TSH, it is less than TA, and relation between TSH and output power is TSH is equal to output power in watts divided by 2 pi n. Again 1 upon 2 pi is 0.159, and therefore TSH is equal to 0.159 output in watts upon n if speed n is in RPS. If it is in RPM, then instead of 0.159, we have to take 9.55 if the speed is in revolutions per minute. Then expression for speed n is equal to EB upon phi into 60A upon ZP, revolutions per minute, if it is in RPM. If it is in RPS, then this 60 will be absent. And therefore, speed n is directly proportional to the back EMF EB and inversely proportional to flux phi. And therefore, as speed is directly proportional to back EMF and inversely proportional to flux, N2 upon N1 is equal to EB2 upon EB1 into phi1 upon phi2. So you are advised to remember all these expressions so that you can solve numerical problems on torque and speed of DC motors. Let us now solve example 1. So the armature of a 4-pole means number of poles P is equal to 4. 220 volt means terminal voltage V or supply voltage V is equal to 220 volt. Lap wound means number of parallel paths A is equal to number of poles P, and therefore A is equal to 4. Has 540 conductors means Z is equal to 540. It takes a current of 32 ampere means load current IL is equal to 32 amperes, and it develops output power of 5.595 kilowatt, means P is equal to 5.595 kilowatt, or it is equal to 5.595 into 10 raised to 3, that is 5595 watt. The field winding takes 1 ampere, means current through field winding IF is equal to 1 ampere. The armature resistance is 0.09 ohm, means Ra is equal to 0.09, and flux per pole is 30 milliweber. So phi is equal to 30 into 10 raised to minus 3 Weber. So this is the given data, and you have to calculate one, the speed, that is N, and second, shaft torque, that is TSH. Now in this case the motor is a DC shunt motor. So the load current is given and field current is given. You can calculate the armature current. So here IA is equal to IL minus IF. Now IL is given as 32 and IF is given as 1. So IA is equal to IL minus IF, which is equal to 32 minus 1, that is 31 ampere. So current in this armature is 31 ampere. So if you know the armature current and armature resistance, you can calculate EB. EB is equal to V minus IA into RA. So let us calculate EB. So EB is equal to V, that is 220, minus IA, that is 31, into RA, that is 0.09. So it is equal to 217.21 volt. So this is EB, but EB is also given by 5Pn into Z upon A volts, and therefore we can substitute the values and calculate N. So EB is 5Pn into Z upon A. Here 60 is absent because the speed N is in RPS, that is revolutions per second. So EB is 217.21. Substituting the values of phi, number of poles, number of armature conductors, and number of parallel paths, we can calculate N. So here N is equal to 13.4 RPS, that is revolutions per second. Now second quantity to be determined is shaft torque. So shaft torque is related to output power. So output power is 5595 watt, and the relation between power and torque is P is equal to 2 pi Nt if N is in revolutions per second, and therefore shaft power P or output power P is equal to 2 pi N TSH. So TSH will be equal to P upon 2 pi N. So it is equal to 5595 divided by 2 pi into N. N is 13.4 revolutions per second. So substituting all the values, we will get TSH as 66.45 Newton meter. Let us now solve the next example. Determine developed torque, means we have to determine armature torque TA and shaft torque, that is TSH, of 220 volt, means supply voltage V is equal to 220 volt, 4 pole, means P is equal to 4, wave wound, means A is equal to 2, DC series motor, so the motor is series type, with 800 armature conductors, means Z is equal to 800, supplying a load of 8.2 kilowatt, means P is equal to 8200 watt, by taking 45 ampere from the supply, means Ia or IL, it is equal to 45 ampere. The flux per pole of 25 milliweber means phi is equal to 25 into 10 raised to minus 3 Weber, and its resistance of armature circuit including series field resistance means Ra plus Rse. It is 0.6 ohm. So Ra plus Rse is equal to 0.6 ohm. So with this given data, we have to calculate Ta and Tsh. So first of all, we can calculate Ta. So Ta is given by armature torque Ta. It is 0.159 phi Pia into Z upon A if speed n is in revolutions per second. So we can calculate Ta by substituting the value of flux, then number of poles, armature current, number of armature conductors, and number of parallel paths. We will get Ta as 286.2 Newton meter. Now we have to calculate the shaft torque. Now the shaft torque and output power are related by equation power P is equal to 2 pi n TSH. So first of all we have to determine n. So n can be determined from EB. So EB can be calculated as EB is equal to V minus IA into RA. In this case, this RA is nothing but RA plus RSE, and RA plus RSE is equal to 0.6 ohm. So substituting the values of V, IA and RA, we can calculate EB, which is equal to 193 volt. Now EB and N are related by equation EB is equal to phi Pn into Z upon A. So we know EB as 193 volt. We know the flux per pole phi, number of poles P, number of armature conductors Z, and number of parallel paths A. So substituting all the values, we can calculate the speed N. So in this case, N is equal to 4.825 revolutions per second. Now we can calculate shaft torque. So shaft torque TSH is equal to power P divided by 2 pi n. So P is 8200 and speed is 4.825 revolutions per second. And therefore shaft torque TSH is equal to 270.48 Newton meter. So you can see that there is a difference between armature torque TA and shaft torque TSH, and TA is greater than TSH. The remaining torque is lost in frictional losses, windage loss and iron loss. Let us solve example 3. A DC shunt motor supplied from a 400 volt supply takes an armature current of 25 ampere and runs at 900 rpm. So this is the case 1. In case 1, V1 is equal to 400 volt, IA1 is equal to 25 ampere and N1 is equal to 900 rpm. In this case, let flux per pole is equal to phi 1. Now calculate the speed at which it will run if supplied from a 230 volt supply taking armature current of 15 ampere. Means in case 2, supply voltage is now reduced to 230 volt. Armature current is reduced to 15 ampere. Then we have to calculate what will be the speed N2. The resistance of armature is 0.8 ohm, means Ra is 0.8, Assume that flux per pole at 230 volt, that is flux in case 2, is equal to 75% of its value at 400 volt. Means in second case flux per pole is 0.75 into 51. Now we know the relation between N2 and N1. N2 upon N1 is equal to EB2 upon EB1 into Phi1 upon Phi2. Now EB2 is V2 minus IA2 into RA, and EB1 is equal to V1 minus IA1 into RA. And we know Phi2 is 0.75 into Phi1. So first of all, we can calculate EB1. So it is 380 volt. We can calculate EB2. It is 218 volt. Then we can write the expression for N2 upon N1. So it is equal to 218 divided by 380 into Phi1 upon 0.7551. So this Phi1 will cancel, and solving this we will get N2, substituting the value of N1. So N2 is equal to 688.4 revolutions per minute, that is RPM. Example 4. The armature current of a series motor is 60 ampere when on full load. Means when the motor is running on full load, IA is equal to 60 ampere. So we can call it as case 1. So in case 1, that is full load condition, IA1 is equal to 60 ampere. Then T1 is equal to torque at full load, and flux per pole, let it is Phi1. Find the new torque, that means the torque in the second case, that is T2, as a percentage of full load torque. Means we have to determine the relation between T2 and T1, or T2 and T full load. The flux for a current of 40 ampere is 70%. So in the second case, IA2 is equal to 40 ampere, and the flux per pole is 70%, means it is equal to 0.7 into Phi1. So these are the two cases, and we have to determine the relation between T2 and T1. Now we know that torque is proportional to the product of flux and armature current. So TA is proportional to phi into Ia. So here torque at full load will be proportional to phi1 into Ia1, and in the second case T2 is proportional to phi2 into Ia2. But in second case phi2 is nothing but 0.751, and therefore torque in the second case T2, it is proportional to 0.751 into Ia2. Now we can take the ratio of two torques, that is T2 upon T full load. It is equal to 0.751 into Ia2 divided by phi1 into Ia1. So phi1 will cancel. Ia2 is 40 ampere and Ia1 is 60 ampere. So substituting the values, we get T2 upon T full load is equal to 0.466, or T2 is equal to 0.466 into torque at full load. Means the torque in the second case is 46.6% of the torque at full load if the current is reduced from 60 ampere to 40 ampere and the flux is reduced to 70% of the original flux. Let us now solve the last numerical problem. A 220 volt DC series motor is running at a speed of 1000 rpm and draws 100 ampere. So supply voltage V is equal to 220 volt. In the first case, N1 is 1000 rpm and armature current IA1 is equal to 100 ampere. Calculate at what speed the motor will run. Means we have to calculate N2 when developing half the torque. Means in second case the torque is one half of the torque in first case. Means T2 is equal to one half of T1 or T2 upon T1 is equal to 1 by 2. Total resistance of armature and field is 0.1 ohm. Means Ra plus Rac. It is equal to 0.1 ohm. Assume that the magnetic field is unsaturated. So before saturation, the flux produced is proportional to current flowing through the field winding. Now in this case, field current is same as armature current because armature and field are connected in series as it is a series motor, and therefore flux produced is proportional to the current flowing through armature, and therefore here phi 1 will be proportional to Ia1 and phi 2 will be proportional to Ia2 because the field is unsaturated. After saturation, this relation is not true because after saturation, flux will remain constant. Now here, armature current in the first case is known, which is 100 ampere. Now let us calculate the armature current in the second case, in which case the torque is half the original torque. So we know that TA is proportional to phi into IA. But in this case, phi is also proportional to IA because the field is unsaturated. And therefore, TA will be proportional to IA into IA. That is IA square. And that's why T1 is proportional to Ia1 square and T2 is proportional to Ia2 square. Now we can take the ratio T2 divided by T1. So T2 upon T1, which is equal to 1 by 2, and it is equal to Ia2 square upon Ia1 square. So T2 upon T1 is equal to Ia2 square upon Ia1 square, which is equal to 1 by 2. Now therefore Ia2 square is equal to T2 upon T1, that is 1 by 2 into Ia1 square. Ia1 is 100. It is 100 and therefore Ia2 square it is equal to 100 square divided by 2, which is equal to 5000, and therefore Ia2 is equal to square root of 5000, which is equal to 70.71 ampere. So if the torque is half of the original torque, then current will reduce to 70.71 ampere. Now we can calculate the back EMF in first and second case. So in the first case, back EMF EB1 is equal to V1 minus Ia1 into Ra. In the first case, Ia1 is 100 ampere and therefore back EMF EB1 is 220 minus 100 into zero point 0.1, that is 210 volt. And in the second case, Ia2 is 70.71 ampere and therefore EB2 is equal to 212.929 volt. Now we know the relation between N2 and N1. So N2 upon N1 is equal to EB2 upon EB1 into phi1 upon phi2. Now we have already calculated EB2 and EB1. Now phi1 it is proportional to Ia1 and phi2 is proportional to Ia2, and substituting the values of EB2, EB1, phi1 and phi2, we can calculate N2, and therefore N2 is equal to 1433.95 revolutions per minute. So the speed will change from 1000 rpm to 1433.95 rpm if the torque is reduced to 50% of the original torque. In our next video, we will see characteristics and applications of different types of DC motors. Thank you.